Leetcode question. Today's question is most stones removed, Leetcode 947. So here's the question. So you're given a 2D plane and there are stones on each space in the grid, which is a 2D plane. And at each turn, you can remove a stone if it's either in the same row or the same column as another stone which has not been removed yet. So after you can remove all the stones that you can, you're supposed to return the maximum number of stones that can be removed after all the operations. So let's restate the question. So essentially, we need to determine how many stones can be maximally removed from a grid with the following condition, which is that we can only remove a stone if there's another stone still present in the grid that is either in the same row or the same column. And the process of removing a stone must be done one after another. So here's the key insight to solving this question. If we can trace the chain from stone 1 to stone n, traveling only vertically or horizontally, not diagonally, removing one stone each time along the way, total of n minus 1 stones can be removed at the end of this operation. So let's see why this works. So let's say we have this grid as follows. All the squares in red are stones. So let's assume we start at the stone marked 1 on the grid here. So we can remove stone number 1 as stone number 2 is on the same row as it is. So and then we move to stone 2. We can remove stone 2 as stone 3 is on the same column as it is. And as after we remove 3, we can remove stone 4 as stone 5 is in the same row as it is. And we can remove stone 5 as row 6 is in the same column as it is. So as we can see, we can traverse the entire grid in this snake-like method until we can remove 10 stones as an example. Notice that when we come to the last stone, which is stone number 11, there are no more stones left in the grid. There are no stones in the same row or same column, so it cannot be removed. So from this, we can kind of understand that if we can trace n minus n stones using this method of traversing only horizontally or vertically, we can remove n minus 1 stones. Okay, one unique circumstance it could be, what if you encounter a rectangle-like shape, as we can see in this figure here, which has 4 rows and 3 columns. We'll start off with removing the first stone in orange. After that is removed, then we notice that the stone on top of it can be removed as well, as it has a stone that is still in the same column as it is. So we go on up in the same method and remove the topmost stone. Now we can remove the stone in the middle of the rectangle, as there is a stone on the right, and we do this till the end. We can repeat this process for the next inner stone, and at the end of the day, you'll notice that you're able to remove a total of 11 stones, as seen in the orange square. As explained earlier, you can't remove the last blue stone. So the key insight is that why this method works is that this is because when we move from one stone to another in some order, as we've established like previously, there is always another stone in the same column or same row, as we always move in straight lines which are either horizontal or vertical. We never move diagonally. So how can we count the number of stones that can be traversed this way? Also, we need to note that it is possible that there could be separate clusters of chains. For example, we have two clusters A and B. So, no stone from A is able to reach any stone from B vertically or horizontally. As such, there are two separate clusters. So our methodology will need to account for the fact that it's possible for there to be two separate clusters. So here is the main approach. So we count the number of connected clusters and the number of stones in each cluster. How this will work in pseudocode terms is that we first begin depth first search from every unvisited stone, and then depth first search will move on to the next stone if it's reachable horizontally or vertically. And then we count the calls to depth first search to count the stones in each cluster. And we can determine that the number of stones removed in each cluster is equal to the size of the cluster minus 1. And then we add up all the stones removed from all the clusters and return the answer. So let's look at the code required to solve this problem. So we will need a visited dictionary in this case to keep track of what stones we visit so we don't visit them again. So for each stone we mark the value in the dictionary for the tuple of the row and column to be false. And we also need to initialize a self.counter, which essentially counts how many times the DFS function is being called, and we initially set it to be 0. So here is the main for loop. So we also set up a variable called rem, which is number of stones removed. And as done in a usual DFS, for every stone in stones, if it's not a stone that's been visited, in this case you can also kind of see visited as like a remove checker. If it's true, it means that the stone has been removed. If it's false, it means the stone has not been removed. And we check the current counter, which is the current state of the counter and what value that currently is. And then we perform the DFS function from this stone. At the end of the day, the self.counter would change and it would add up the size of the new cluster that we have found. So we add on self.counter minus current counter minus 1 to rem, and at the end of all the iterations of the for loop, rem will return the correct number of stones that can be removed. Note here that once again we have to minus 1 from self.counter minus current counter, as the last stone cannot be removed in each cluster. So here is the main for loop. So initially we need to increment self.counter by 1 every time we come into this for loop, and we also mark the stone to be true, as in it's removed. So we go through every stone in the original array, and then we note that if it's in the same row as the current stone that we are DFSing from, and the stone has not been visited, we DFS into that stone as well. And we do that for the same column as well. So we have two if conditions to check whether like another stone in the area is the same row, the same column. And note that we will not traverse stones that already been captured before, as we already check for whether they're visited or not. So let's analyze the time space complexity of this operation. A time complexity in this case will be O of n, as we are DFSing only once, and we have visited dictionary which checks whether stone has been visited. And yeah, so essentially we only cover the entire range of stones once, so the time complexity will be O of n. And for space complexity, it will be O of n as well, as we do have a dictionary which stores the visited states for all the stones. So that will be O of n as well. So yeah, so that's the end of today's Leetcode question. Thank you for watching. Bye bye.